who brings Theo his forward and write unit tests for library.addMember and system.addMember. Joe, I agree with you. Please start with library.addMember. Theo, library.addMember is quite similar to usermanagement.addMember, so I guess I'll write similar test cases. Joe, in fact, that won't be required. As I told you when we wrote unit tests for a query, when you write a unit test for a function, you can assume that the functions down the tree work as expected. Theo, right, so I'll just write the test case for existing members. Joe, go for it. Theo starts with a copy and paste of the code from the usermanagement.addMember test case with the existing members in listing 6.23. After a few modifications, the unit test for library.addMember is ready. Joe, beautiful. Now we're ready for the last piece. Write a unit test for system.addMember. Before you start, could you please describe the input and the output of system.addMember? Theo takes another look at the code for system.addMember and hesitates. He's a bit confused. The function doesn't seem to return anything. Theo, the input of system.addMember is a system state instance and a member, but I'm not sure what the output of system.addMember is. Joe, in fact, system.addMember doesn't have any output. It belongs to this stateful part of our code that doesn't deal with data manipulation. Although DOP allows us to reduce the size of the stateful part of our code, it still exists. Here is how I visualize it. Joe calls the waiter to see if he can get more napkins. With that problem resolved, he draws the diagram in figure 6.7. Theo, then how do we validate that the code works as expected? Joe, we'll retrieve the system state after the code is executed and compare it to the expected value of the state. Theo, okay, I'll try to write the unit test. Joe, writing unit tests for stateful code is more complicated than for data manipulation code. It requires the calm of the office. Theo, then let's go back to the office. Waiter, check please. Theo picks up the tab, and he and Joe take the cable car back to Albatross. When they're back at the office, Theo starts coding the unit test for library.addMember. Theo, can we use _.isEqual with system state? Joe, definitely. The system state is a map like any other map. Tip. The system state is a map. Therefore, in the context of a test case, we can compare the system state after a mutation is executed to the expected system state using _.isEqual. Theo copies and pastes the code for library.addMember, listing 6.21, which initializes the data for the test. Then he passes a system state object that is initialized with library state before to system.addMember. Finally, to complete the test, he compares the system state after the mutation is executed with the expected value of the state. Joe, wow, I'm impressed. You did it. Congratulations. Theo, thank you. I'm so glad that in DOP most of our code deals with data manipulation. It's definitely more pleasant to write unit tests for stateless code that only deals with data manipulation. Joe, now that you know the basics of DOP, would you like to refactor the code of your Clapham prototype according to DOP principles? Theo, definitely. Nancy told me yesterday that Clapham is getting nice market traction. I'm supposed to have a meeting with her in a week or so about the next steps. Hopefully, she'll be willing to work with Albatross for the long term. Joe, exciting. Do you know what might influence Nancy's decision? Theo, our cost estimate, certainly, but I know she's in touch with other software companies. If we come up with a competitive proposal, I think we'll get the deal. Joe, I'm quite sure that after refactoring to DOP, features will take much less time to implement. That means you should be able to quote Nancy a lower total cost than the competition, right? Theo, I'll keep my fingers crossed. Moving forward. The meeting with Nancy went well. Albatross got the deal. Monica, Theo's boss, is pleased, and it's going to be a long-term project with a nice budget. They'll need to hire a team of developers in order to meet the tough deadlines. While driving back to the office, Theo gets a phone call from Joe. Joe, how was your meeting with Nancy? Theo, we got the deal. Joe, awesome. I told you that with DOP the cost estimation would be lower. Theo, in fact, we're not going to use DOP for this project. Joe, why? Theo, after refactoring the library management system prototype to DOP, I did a deep analysis with my engineers. We came to the conclusion that DOP might be a good fit for the prototype phase, but it won't work well at scale. Joe, could you share the details of your analysis? Theo, I can't right now, I'm driving. Joe, could we meet in your office later today? Theo, I'm quite busy with the new project and the tough deadlines. Joe, let's meet at least in order to have a proper farewell. Theo, okay, let's meet at 4 p.m. then. Note: the story continues in the opener of Part 2. Summary: most of the code in a data-oriented system deals with data manipulation. It's straightforward to write unit tests for code that deals with data manipulation. Test cases follow the same simple general pattern. A. Generate data input. B. Generate expected data output. C. Compare the output of the function with the expected data output. In order to compare the output of a function with the expected data output, we need to recursively compare the two pieces of data. The recursive comparison of two pieces of data is implemented via a generic function. When a function returns a JSON string, we parse the string back to data so that we deal with data comparison instead of string comparison. A tree of function calls for a function f is a tree where the root is f, and the children of a node g in the tree are the functions called by g. The leaves of the tree are functions that are not part of the code base of the application and are functions that don't call any other functions. The tree of function calls visualization guides us regarding the quality and quantity of the test cases in a unit test. Functions that appear in a lower level in the tree of function calls tend to involve less complex data than functions that appear in a higher level in the tree. Functions that appear in a lower level in the tree of function calls usually need to be covered with more test cases than functions that appear in a higher level in the tree. Unit tests for mutations focus on the calculation phase of the mutation. The validity of the data depends on the context. The smaller the data, the easier it is to manipulate. We compare the output and the expected output of our functions with a generic function that recursively compares two pieces of data. For example, _.isEqual. When we write a unit test for a function, we assume that the functions called by this function are covered by the unit tests and work as expected. This significantly reduces the quantity of test cases in our unit tests. We avoid using string comparison in unit tests for functions that deal with data. Writing a unit test for the main function of a mutation requires more effort than for a query. Remember to include negative test cases in your unit tests. The system state is a map. Therefore, in the context of a test case, we can compare the system state after a mutation is executed to the expected system state using a generic function like _.isEqual. Part 2. Scalability. Theo feels a bit uncomfortable about the meeting with Joe. He was so enthusiastic about DOP and he was very good at teaching it. Every meeting with him was an opportunity to learn new things. Theo feels a lot of gratitude for the time Joe spent with him. He doesn't want to hurt him in any fashion. Surprisingly, Joe enters the office with the same relaxed attitude as usual, and he is even smiling. Joe, I'm really glad that you got the deal with Nancy. Theo, yeah, there's lots of excitement about it here in the office, and a bit of stress, too. Joe, what kind of stress? Theo, we need to hire a team of developers, and the deadlines are quite tight. Joe, but you told me that you won't use DOP. I assume that you gave regular deadlines. Theo, no, my boss Monica really wanted to close the deal. She feels that success with this project is strategically important for Albatross, so it's worthwhile to accept some risk by giving what she calls an optimistic time estimation. I told her that it was really an unrealistic time estimation, but Monica insists that if we make smart decisions and bring in more developers, we can do it. Joe: I see. Now I understand why you told me over the phone that you were very busy. Anyway, would you please share the reasons that made you think DOP wouldn't be a good fit at scale? Theo: First of all, let me tell you that I feel a lot of gratitude for all the teaching you shared with me. Re-implementing the Clafim prototype with DOP was really fun and productive due to the flexibility this paradigm offers. Joe: I'm happy that you found it valuable. Theo: But, as I told you over the phone, now we're scaling up into a long-term project with several developers working on a large code base. We came to the conclusion that DOP will not be a good fit at scale. Joe: Could you share the reasons behind your conclusion? Theo: There are many of them. First of all, as DOP deals only with generic data structures, it's hard to know what kind of data we have in hand, while in OOP, we know the type of every piece of data. For the prototype, it was kind of okay, but as the code base grows and more developers are involved in the project, it would be too painful. Joe: I hear you. What else, my friend? Theo: Our system is going to run on a multi-threaded environment. I reviewed the concurrency control strategy that you presented, and it's not thread safe. Joe: I hear you. What else, my friend? Theo: I have been doing a bit of research about implementing immutable data structures with structural sharing. I discovered that when the size of the data structure grows, there is a significant performance hit. Joe: I hear you. What else? Theo: As our system grows, we will use a database to store the application data and external services to enrich book information. And in what you have showed me so far, data lives in memory. Joe: I hear you. What else, my friend? Theo: Don't you think I have shared enough reasons to abandon DOP? Joe: I think that your concerns about DOP at scale totally make sense. However, it doesn't mean that you should abandon DOP. Theo: What do you mean? Joe: With the help of meditation, I learned not to be attached to the objections that flow in my mind while I'm practicing. Sometimes all that is needed to quiet our minds is to keep breathing. Sometimes a deeper level of practice is needed. Theo: I don't see how breathing would convince me to give DOP a second chance. Joe: Breathing might not be enough in this case, but a deeper knowledge of DOP could be helpful. Until now, I have shared with you only the material that was needed in order to refactor your prototype. In order to use DOP in a big project, a few more lessons are necessary. Theo: But I don't have time for more lessons. I need to work. Joe: Have you heard the story about the young woodcutter and the old man? Theo: No. Joe: It goes like this. The young woodcutter and the old man. A young woodcutter strained to saw down a tree. An old man, who was watching nearby, asked, "What are you doing?" "Are you blind?" the woodcutter replied. "I'm cutting down this tree." The old man replied, "You look exhausted. Take a break. Sharpen your saw." The young woodcutter explained to the old man that he had been sawing for hours and did not have time to take a break. The old man pushed back. "If you sharpen the saw, you would cut down the tree much faster." The woodcutter said, "I don't have time to sharpen the saw. Don't you see? I'm too busy." Theo takes a moment to meditate on the story. He wonders if he needs to take the time to sharpen his saw and commit to a deeper level of practice. Theo: Do you really think that with DOP it will take much less time to deliver the project? Joe: I know so. Theo: But if we miss the deadline, I will probably get fired. I'm the one that needs to take the risk, not you. Joe: Let's make a deal. If you miss the deadline and get fired, I will hire you at my company for double the salary you make at Albatross. Theo: And what if we meet the deadline? Joe: If you meet the deadline, you will probably get promoted. In that case, I will ask you to buy a gift for my son Nariah and my daughter Aurelia. Theo: Deal. When will I get my first lesson about going deeper into DOP? Joe: Why not start right now? Theo: Let me reschedule my meetings. Chapter 7. Basic Data Validation. A solemn gift. This chapter covers the importance of validating data at system boundaries, validating data using the JSON schema language, integrating data validation into an existing codebase, getting detailed information about data validation failures. At first glance, it may seem that embracing DOP means accessing data without validating it and engaging in wishful thinking, where data is always valid. In fact, data validation is not only possible, but recommended when we follow data-oriented principles. This chapter illustrates how to validate data when data is represented with generic data structures. It focuses on data validation occurring at the boundaries of the system, while in Part 3, we will deal with validating data as it flows through the system. This chapter is a deep dive into the fourth principle of DOP. Principle number 4. Separate data schema from data representation. Section 7.1. Data validation in DOP. Theo has rescheduled his meetings. With such an imposing deadline, he's still not sure if he's made a big mistake giving DOP a second chance. Note: the reason why Theo rescheduled his meetings is explained in the opener for Part 2. Take a moment to read the opener if you missed it. Joe: what aspect of OOP do you think you will miss the most in your big project? Theo: data validation. Joe: can you elaborate a bit? Theo: in OOP, I have this strong guarantee that when a class is instantiated, its member fields have the proper names and proper types. But with DOP, it's so easy to have small mistakes in field names and field types. Joe: well, I have good news for you. There is a way to validate data in DOP. Theo: how does it work? I thought DOP and data validation were two contradictory concepts. Joe: not at all. It's true that DOP doesn't force you to validate data, but it doesn't prevent you from doing so. In DOP, the data schema is separate from the data representation. Theo: I don't get how that would eliminate data consistency issues. Joe: according to DOP, the most important data to validate is data that crosses the boundaries of the system. Theo: which boundaries are you referring to? Joe: in the case of a web server, it would be the areas where the web server communicates with its clients and with its data sources. Theo: a diagram might help me see it better. Joe goes to the whiteboard and picks up the pen. He then draws a diagram like the one in Figure 7.1. Joe: this architectural diagram defines what we call the boundaries of the system in terms of data exchange. Can you tell me what the 3 boundaries of the system are? Note: the boundaries of a system are defined as the areas where the system exchanges data. Theo: let me see. The first one is the client boundary. Then we have the database boundary, and finally the web service boundary. Joe: exactly. It's important to identify the boundaries of a system because in DOP we differentiate between 2 kinds of data validation: validation that occurs at the boundaries of the system and validation that occurs inside the system. Today we're going to focus on validation that occurs at the boundaries of the system. Theo: does that mean data validation at the boundaries of the system is more important? Joe: absolutely. Once you've ensured that data going into and out of the system is valid, the odds for an unexpected piece of data inside the system are pretty low. Tip: when data at system boundaries is validated, it's not crucial to validate data again inside the system. Theo: why do we need data validation inside the system then? Joe: it has to do with making it easier to code your system as your code base grows. Theo: and what's the main purpose of data validation at the boundaries? Joe: to prevent invalid data from going in and out of the system, and to display informative errors when we encounter invalid data. Let me draw a table on the whiteboard so you can see the distinction. Table 7.1. Theo: when will you teach me about data validation inside the system? Joe: later, when the code base is bigger. Section 7.2, JSON Schema in a Nutshell. Theo. For now, the library management system is an application that runs in memory with no database and no HTTP clients connected to it. But Nancy will probably want me to make the system into a real web server with clients, database, and external services. Joe. Okay, let's imagine how a client request for searching books would look. Theo. Basically, a search request is made of a string and the fields you'd like to retrieve for the books whose title contains the string. So the request has two fields, title, which is a string, and fields, which is an array of strings. Theo quickly writes on the whiteboard. When he finishes, he steps aside to let Joe view his code for a search request. Joe. I see. Let me show you how to express the schema of a search request separately from the representation of the search request data. Theo. What do you mean exactly by separately? Joe. Data representation stands on its own, and the data schema stands on its own. You are free to validate that a piece of data conforms with a data schema as you will and when you will. Tip. In DOP, the data schema is separate from the data representation. Theo. It's a bit abstract for me. Joe. I know. It will become much clearer in a moment. For now, I'm going to show you how to build the data schema for the search request in a schema language called JSON schema. Theo. I love JSON. Note. Information on the JSON schema language can be found at json-schema.org. The schemas in this book use JSON schema version 2020-12. Joe. First, we have to express the data type of the request. What's the data type in the case of a book search request? Theo. It's a map. Joe. In JSON schema, the data type for maps is called object. Look at this basic skeleton of a map. It's a map with two fields, type and properties. Joe goes to the whiteboard. He quickly writes the code for the map with its two fields. Joe. The value of type is object, and the value of properties is a map with the schema for the map fields. Theo. I assume that inside properties, we are going to express the schema of the map fields as JSON schema. Joe. Correct. Theo. I am starting to feel the dizziness of recursion. Joe. In JSON schema, a schema is usually a JSON object with a field called type, which specifies the data type. For example, the type for the title field is string and Theo. The type for the fields field is array. Joe. Yes. Now it's Theo's turn to go to the whiteboard. He fills the holes in the search request schema with the information about the fields. On Theo's way back from the whiteboard to his desk, Joe makes a sign with his right hand that says, "Stay near the whiteboard, please." Theo turns and goes back to the whiteboard. Joe. We can be a little more precise about the fields property by providing information about the type of the elements in the array. In JSON schema, an array schema has a property called items, whose value is the schema for the array elements. Without any hesitation, Theo adds this information on the whiteboard. Stepping aside, he shows Joe the result. Before going back to his desk, Theo asks Joe, Theo, are we done now? Joe. Not yet. We can be more precise about the fields field in the search request. I assume that the fields in the request should be part of a closed list of fields. Therefore, instead of allowing any string, we could have a list of allowed values. Theo. Like an enumeration value? Joe. Exactly. In fact, JSON schema supports enumeration values with the enum keyword. Instead of an object with a property type string, you need to have an object with a property type enum that's an array, and replace the dots with the supported fields. Once again, Theo turns to the whiteboard. He replaces the dots with the information Joe requests. Theo. Are we done now? Joe. Almost. We need to decide whether the fields of our search request are optional or required. In our case, both title and fields are required. Theo. How do we express this information in JSON schema? Joe, there is a field called required, whose value is an array made of the names of the required fields in the map. After adding the required field, Theo looks at Joe. This time he makes a move with his right hand that says, "Now you can go back to your desk." Joe, now I'll show you how to validate a piece of data according to a schema. Theo, what do you mean, validate? Joe, validating data according to a schema means checking whether data conforms to the schema. In our case, it means checking whether a piece of data is a valid search book's request. Tip. Data validation in DOP means checking whether a piece of data conforms to a schema. Theo, I see. Joe, there are a couple of libraries that provide JSON schema validation. They have a validate function that receives a schema and a piece of data and returns true when the data is valid and false when the data is not valid. I just happen to have a file in my laptop that provides a table with a list of schema validation libraries. Table 7.2. We can print it out if you like. Theo turns on the printer as Joe scans through his laptop for the table. When he has it up, he checks with Theo and presses print. Theo, so if I call validate with this search request and that schema, it will return true? Theo indicates the search request example from listing 7.7 and the schema from listing 7.6. Joe, give it a try and you'll see. Indeed, when Theo executes the code to validate the search request, it returns true. Joe, now please try an invalid request. Theo, let me think about what kind of invalidity to try. I know, I'll make a typo in the title field and call it tilde with the L before the T. As expected, the code with the type returns false. Theo is not surprised, and Joe is smiling from ear to ear. Theo, the syntax of JSON schema is much more verbose than the syntax for declaring the members in a class. Why is that so? Joe, for two reasons. First, because JSON schema is language independent. It can be used in any programming language. As I told you, there are JSON schema validators available in most programming languages. Theo, I see. Joe, second, JSON schema allows you to express validation conditions that are much harder, if not possible, to express when data is represented with classes. Tip. The expressive power of JSON schema is high. Theo, now you have triggered my curiosity. Can you give me some examples? Joe, in a moment we'll talk about schema composition. Someday I'll show you some examples of advanced validation. Note: advanced validation is covered in Chapter 12. Theo, what kind of advanced validation? Joe, what I mean by advanced validation is, for instance, validating that a number falls within a given range, or validating that a string matches a regular expression. Theo, is there a way to get details about why the request is invalid? Joe, absolutely. I'll show you later. For now, let me show you how to make sure the response the server sends back to the client is valid. Theo, it sounds much more complicated than a search book request. Joe, why? Theo, because a search response is made of multiple book results, and in each book result, some of the fields are optional. Section 7.3, Schema Flexibility and Strictness. Joe, can you give me an example of what a book search response would look like? Theo, take a look at this example. It's a search response with information about two books, 7 Habits of Highly Effective People and The Power of Habit. Joe, it's funny that you mentioned the power of habit. I'm reading this book in order to get rid of my habit of biting my nails. Anyway, what fields are required and what fields are optional in a book search response? Theo, in book information, the title and available fields are required. The other fields are optional. Joe, as I told you when we built the schema for the book search request, fields in a map are optional by default. In order to make a field mandatory, we have to include it in the required array. I'd probably implement it with something like this. Tip. In JSON schema, map fields are optional by default. Theo, I must admit that specifying a list of required fields is much simpler than having to specify that a member in a class is nullable. Joe, agreed. Theo, on the other hand, I find the nesting of the book information schema in the search response schema a bit hard to read. Joe, nothing prevents you from separating the book information schema from the search response schema. Theo, how? Joe, it's just JSON, my friend. It means you are free to manipulate the schema as any other map in your program. For instance, you could have the book information schema in a variable named bookInfoSchema and use it in the search book's response schema. Let me refactor the schema to show you what I mean. Theo, once again, I have to admit that JSON schemas are more composable than class definitions. Tip. JSON schemas are just maps. We are free to compose and manipulate them like any other map. Joe, let's move on to validating data received from external data sources. Theo, is that different? Joe, not really, but I'll take it as an opportunity to show you some other features of JSON schema. Theo, I'm curious to learn how data validation is used when we access data from the database. Joe, each time we access data from the outside, it's a good practice to validate it. Can you show me an example of how a database response for a search query would look? Tip. It's a good practice to validate data that comes from an external data source. Theo, when we query books from the database, we expect to receive an array of books with 3 fields: title, ISBN, and available. The first 2 values should be strings, and the third one should be a Boolean. Joe, are those fields optional or required? Theo, what do you mean? Joe, could there be books for which some of the fields are not defined? Theo, no. Joe, in that case, the schema is quite simple. Would you like to try writing the schema for the database response? Theo, let me see. It's an array of objects where each object has 3 properties, so something like this. Joe, well done, my friend. Now I want to tell you about the additional properties field in JSON schema. Theo, what's that? Joe, take a look at this array. Joe, is it a valid database response? Theo, no. A database response should not have a dummy_property field. It should have only the 3 required fields specified in the schema. Joe, it might be surprising, but by default, fields not specified in the schema of an object are allowed in JSON schema. In order to disallow them, one has to set additional properties to false, like this. Tip. In JSON schema, by default, fields not specified in the schema of a map are allowed. Theo, why is that? Joe, the reason is that usually having additional fields in a map doesn't cause trouble. If your code doesn't care about a field, it simply ignores it. But sometimes we want to be as strict as possible, and we set additional properties to false. Theo, what about the search request and response schema from the previous discussions? Should we set additional properties to false? Joe, that's an excellent question. I'd say it's a matter of taste. Personally, I like to allow additional fields in requests and disallow them in responses. Theo, what's the advantage? Joe, well, the web server is responsible for the responses it sends to its clients. It makes sense then to be as strict as possible. However, the requests are created by the clients, and I prefer to do my best to serve my clients even when they are not as strict as they should be. Theo, naturally, the client is always right. Joe, actually, I prefer the way John Postel formulated his robustness principle. Be conservative in what you send, be liberal in what you accept. Tip. It's a good practice to be strict with the data that you send and to be flexible with the data that you receive. Section 7.4, Schema Composition. Theo, what about validating data that comes from an external web service? Joe, can you give me an example? Theo, In the near future, we'll have to integrate with a service called Open Library Books API that provides detailed information about books. Note: for information on the Open Library Books API, see openlibrary.org/dev/docs/API/books. Joe, can you show me, for instance, the service response for Watchman? Theo, sure, here you go. Theo taps a few keys on his keyboard and brings up the response. Joe looks at the JSON for a long time. Theo asks himself, what could be so special in this JSON? While Joe is meditating about this piece of JSON, Theo writes the JSON schema for the Books API response. It doesn't seem to be more complicated than any of the previous schemas. When Theo is done, he asks Joe to take a look at the schema. Joe, good job. Theo, that wasn't so hard. I really don't see why you looked at this JSON response for such a long time. Joe, well, it has to do with the ISBN_10 and ISBN_13 fields. I assume that they're not both mandatory. Theo, right. That's why I didn't include them in the required field of my schema. Joe, but one of them should always be there, right? Theo, sometimes one of them and sometimes both of them. Like for Watchmen. It depends on the publication year of the book. Books published before 2007 have ISBN_10, and books published after 2007 have ISBN_13. Joe, oh, I see. And Watchmen has both because it was originally published in 1986, but published again after 2007. Theo, correct. Joe, then you need your schema to indicate that one of the ISBN fields is mandatory. That's a good opportunity for me to tell you about JSON schema composition. Theo, what's that? Joe, it's a way to combine schemas, similarly to how we combine logical conditions with and, or, and not. Theo, I'd like to see that. Joe, sure. How would you express the schema for the Books API response as a composition of three schemas? Basic book info schema, the schema that you wrote where only title is required, mandatory ISBN 13, a schema where only ISBN_13 is required, and mandatory ISBN 10, a schema where only ISBN_10 is required. Theo, I think it should be basic book info schema and mandatory ISBN 13 or mandatory ISBN 10 in parentheses. Joe, exactly. The only thing is that in JSON schema we use all of instead of and any of instead of or. Joe shows Theo the result in listing 7.18 and an example of its usage in listing 7.19. Theo, I see why they call it all of and any of. The first one means that data must conform to all the schemas, and the second one means that data must conform to any of the schemas. Joe, yep. Note: JSON schema also supports one of for cases where data must be valid against exactly one schema. Theo, nice. With schema composition, JSON schema seems to have more expressive power than what I was used to when representing data with classes. Joe, that's only the beginning. I'll show you more data validation conditions that can't be expressed when data is represented with classes some other time. Note: advanced data validation is covered in Chapter 12. Theo, something still bothers me though. When data isn't valid, you don't know what went wrong. Section 7.5. Details about data validation failures. Joe, so far we've treated JSON schema validation as though it were binary. Either a piece of data is valid or it isn't. Theo, right. Joe, but in fact, when a piece of data is not valid, we can get details about the reason of the invalidity. Theo, like when a required field is missing, can we get the name of the missing field? Joe, yes. When a piece of data is not of the expected type, we can get information about that also. Theo, that sounds very useful. Joe, indeed. Let me show you how it works. Until now, we used a generic validate function, but when we deal with validation failures, we need to be more specific. Theo: why? Joe: because each data validator library has its own way of exposing the details of a data validation failure. For instance, in JavaScript AJV, the errors from the last data validation are stored as an array inside the validator instance.